Hello world, it's Craig. A fairly common question I get is about my workflow for my 8008, 8080, and 8085 assembly language projects. So in this video, I'm going over my programming process for these systems, like for the MCS 85 minimum system, the STK 85, the SBC 85, or the STD 85. I'm going to start with the text editor, but most of this is going to be on the assembler, including some of my favorite features that make my life so much easier. Now you can use any text editor you like, and as long as it has existed, I've been happy enough with just using Notepad. The only requirement is that the editor must not embed any control characters or special headers or anything else other than the pure ASCII text that you're entering. If you want something more sophisticated, Notepad++ has a lot of nice features. It can be aggravating, but it offers these features and has a fancier user interface, and actually I wind up using it most of the time. I select the language as assembly so it can help me see what's going on in the code. And then when looking at Intel hex files, you select the language as Intel hex, and it color codes the byte count, the starting address, data type, data and checksum, and it just makes it easier to read and catch mistakes. When I'm creating files, source code, as far as the file extension, I usually use A08 for 8008 code, A80 or A85, depending if it's specific to either of those two processors. So for example, this is my double-dabble binary to BCD utility routine. I showed this in an earlier video. And while I'm looking at this file, in that double-dabble video, a commenter, Pince128, found some lazy bytes that were not doing anything in the code. So rather than the 68 bytes that I had, he could do it in 62 bytes. So well done. My preferred assembler is William Cawley's A85. Specifically, I use the version maintained by Herb Johnson because Herb is really good about adding little features that I request now and again. For 8008 code, I use A08, which Herb Johnson also has a copy that he maintains on his website. And these are both available for download. These assemblers are not fancy or loaded with whiz-bang features, but they are very good, capable tools. I'll put a link to Herb Johnson's site for the A85 and A08 assemblers, and you can download them from there. If you get these from Herb, it would be nice if you drop him a note. I'm sure he'd appreciate it. And also, for the next time that I want to ask Herb to add a feature to the assembler, it'd probably help my case if you tell him that I'm the one that sent you there. So for example, I'd really like Herb to add the ability to define a record type and write that to the hex file along with an argument so that I don't have to manually add my execute record that I mentioned in the last couple of videos. So after you download the assembler, you simply unzip everything in the destination folder, and then add that folder to your path and the Windows system environment variables, and that way Windows can find the assembler on its own no matter what folder you're in when you invoke the assembler. Of course, look over the documentation that comes with the assembler. It's not that long of a document, and you just might find something in there that makes your life much, much simpler. When I start a new project, I copy over a batch file that runs the command line to assemble whatever project I'm working on and then open up the list file. Normally, I just name it asm.bat and update it to the file names of whatever I'm working on at that time. So here's the batch file to invoke A85 for the double-dabble utility. A85 is the assembler, and then this is the input file name. If there were spaces in the file name, then the input file name would need to be enclosed in quotations. Then these are the outputs. The list output is just abbreviated with a .lst extension. The output, which is the Intel hex file, has a .hex extension, and the symbol file, the sym extension. Now the list file is just the original code and comments, but it includes the calculated values of any expressions, any memory references such as those in calls and jumps. It also has the instruction value for the opcodes and memory location of everything. The Intel hex file is what we'll either download to the platform directly or give to the EEPROM programmer to put into a program. And then the symbol file we'll talk about in just a minute. In this batch file, after the assembly completes, the next line in the batch file opens the output file in whatever text editor I happen to have assigned to that extension, like Notepad++. So in practice, I'm in the project folder. I simply open a command prompt, right-click on either select Open in Terminal or go to More Options and select Open a Command window here if that's your preference. Then I just type ASM to start the batch file. The batch file invokes the assembler with all the command line inputs. Then when the assembler is done, the batch file opens whatever output files I've specified. Usually I just want the list file, but sometimes I have it open the symbol or the output hex files if I'm looking for something in particular. So now I can look at the errors in the list file, fix them in the source file, save the source file, go back over to the command window I left open, give it an up arrow to reload the last command line, and then reassemble. Now after it assembles and when you go back to Notepad++, it'll ask you if you want to update to the newer version of the file. It'll say somebody else changed this, do you want to update? This is your last chance to read what it's asking and to notice that if you accidentally made the edits in the list file and not in the source file. Don't think I haven't made that mistake many, many times. I do want to point out two of the latest features in the assembler that I asked Herb to add, and they really improve the assembler and make code cleaner and easier to manage. The first one is the creation of the symbol file that I mentioned earlier. So symbols and their values are already found at the bottom of the list file. But the symbol file is a standalone file which also includes the symbol name and value of all the symbols that were created by the assembler. These symbols may be variables that were calculated or labels that have addresses. But the big difference between the symbols at the bottom of the list file and the ones in the symbol file is that in the symbol file, there's an assignment of each symbol back to its value, meaning each symbol, there's an equals, EQU pseudo opcode, and then the value of that symbol. So for example, here's the symbol file for the resident monitor in the SDK85+. So now that we have this symbol file, we can use it in later programs that we create, and it will include all of those symbols and labels that were previously defined in that earlier program. And then we can reference those labels by name in our program. So for example, if we're writing code that's going to run on one of these platforms that has a resident monitor, that resident monitor is full of useful utilities that it needs, but the utilities can also be used by our program that we're going to download and run on that platform along with the resident monitor. So when we want to call a routine or use a variable or reference a memory location that was defined in the resident monitor, it's not necessary for us to go looking for where that routine is located and explicitly add it to our program. The address of that routine will be included in the symbol file that was created when I assembled the SDK85 monitor. All we need to do is add that resident monitor symbol file to the top of our code, and those symbols are now ours to use. Easiest way to do that is assembler has an include pseudo opcode that'll open any file and include that file at that location in the source code during assembly. And it's just as if that file were copied and pasted into the source code. And I also use the include opcode to bring in other things like the ASCII definition file. And you'll find the ASCII definition file in nearly all of my programs, and it lets me use common names for the ASCII control characters. For example, I don't need to remember that the hex value for an escape. I can just put in ESC in my code, and the assembler replaces that with the ASCII value. It makes coding much more readable and less prone to errors. Here in that part of the list file is the monitor symbol that was brought into the source and assembled. This gives us the value for every label or variable that was used in the monitor for this SDK85. Now below that is the include ASCII definitions for the control characters. You'll see here in a bit that in my code, I utilize the routine that's in the SDK monitor that outputs values to the display. They're upddt to update the data field and updad to update the address field. So here are those two labels defined in the symbol table, and those are at address 036E and address 0363. Now we can look in the SDK user's manual where it talks about how to use these routines and where they're located. Without the symbol file, if we wanted to use these routines, I'd either need to define their address somewhere in my program, create the symbol from scratch, or I would need to hard code it in the instructions when I call those routines. But with the symbol file, that's all taken care of for us. In my source code, I call those routines along with the read keyboard routine that's also in the SDK monitor. So the SDK monitor routines are now called just like the routines that I have in my code. With the symbol file, there really isn't any difference between using code that's already on the platform and code that I'm now running on the platform. So it's very similar to file linking, when you would assemble all your source code and then link them where they would get the labels from each other, and then you would locate that resulting file. Here it is done sequentially and at assembly time, so you can't have any back dependencies, but I can live without that. Include isn't a new feature. It's been in AE85 since the beginning, I presume. But I think I asked Herb for the symbol file end of 2022. We exchanged a few emails to come up with the format, and within a month or two, lo and behold, Herb sent me an update assembler that had the symbol switch in the command line to create the symbol file. And I've been using that feature nearly every day since then. So if you're watching Herb, thank you for adding that. It's really improved the way that I do my programming. However, as useful as it is, there's a drawback with including all of these symbols, and most of them which we aren't even using. The listings start to get very long and can go on and on for pages. So along with the symbol file, Herb added the list on, list off pseudo opcode, which is found in a lot of assemblers. So right before the includes of the symbol file and the ASCII definition, there's a list off pseudo opcode, and afterwards I include a list on pseudo opcode. It was commented out for the demonstration, but let me uncomment that list off and then reassemble. So now the entire symbol file and ASCII definitions are suppressed. They're still there, of course, and if there was code in there, it would be assembled in, but the file contents are just being hidden from the listing. So while it's convenient to be able to turn these lists off, you must remember that if there's an error that you simply cannot find, it could be in the part of the listing that you turned off. So use list off with care. Now note that the symbol file uses equate, the EQU, to assign the value to the label rather than the set. Now equate only lets you assign the symbol once, where set lets it be redefined multiple times. We intentionally used the EQU so that the assembler would throw an error if we tried to redefine something. But just remember that if you can't find those pesky multiple definition errors, it may be in the symbol file that you then hid with the list off and you forgot about it. In a lot of my programs, you'll notice that I use a program counter symbol, which is the $sign. This symbol returns the current value of the program counter. So for example, if the program began with a label called start, if you create a label called length equals $sign minus start, it'll return the number of bytes between start and this location. And I use the program counter symbol for all sorts of calculations, including to tell me how many bytes I have left in my EEPROM. And remember that symbol file from the program you're working on will include the symbols from any symbol files that you included in previous programs, plus all of the symbols added by your current program. And so then you can use that single symbol file for the next program that's running on the platform. As an example of that, in many of my platforms, I have a utility prom that is full of my most useful utilities. This SDK Plus, for example, it has a monitor ROM in the base socket and then a utility ROM in the 8755 socket. When I assembled that utility ROM, I included the symbol file from the host monitor program. And then that utility ROM created a symbol file that includes everything, and that's what I use when I'm creating other programs that I'm then going to run on this platform. So it's a poor man's linker. It allows me to link and include all dependencies of all my code at one time. I didn't call it out specifically, but when I include things like the monitor symbol file or the ASCII definition file and so forth, I include them with the full path name so that they always go back to the master copy and I don't have outdated copies all over. I just select the file, right-click to copy the path name, and paste it into my source code. It automatically adds the quotations around the path name. That way, whenever I update the utility EEPROM and it creates a new symbol file, then the latest symbol file is automatically used for the latest program. Of course, if I update the actual monitor, then I need to assemble that and then assemble the utility ROM and then assemble anything else that was dependent on those symbol files going all the way back. The last thing I'm going to show you that I really use a lot in the assembler is the conditional assembly pseudo opcode if else endif. This is very important. These may look like they're at the very left edge. Like all opcodes and pseudo opcodes, there needs to be some white space first, but I prefer the look of the if else endif being towards the left. So I don't tab in for those, there's just a single white space. So don't put them at the beginning of a line and wonder why the assembler throws an error. The format is if and a statement. If that statement is non-zero, then it does what is directly after the if. If that statement is zero, then it assembles what comes after the else. You don't need to use the else, but you have to end with an endif. So here, for example, I have a label RAM, which I set to 0 if I want to go to this into the EEPROM, and I set it to 1 if I want it to go into the 8155 RAM. And I use that like when I'm debugging the code. That RAM assembler directive is up at the top of the code where it's easy to find and change. So if that label RAM is set to 0, this first org is completely ignored, and the org after the else is used to locate the code in the ZIF socket. Here's a little tip when I'm assembling programs that are very tight, so going into a 1702 or a 2708 or something like that. I'll put an if endif at the end of the program with an expression using the program counter symbol that will evaluate true if the program won't fit in the EEPROM. I then put something within the if endif that'll generate an error when that expression is true. And that way, when I assemble, right away I can see if I've gone past the end of the EEPROM. There's no use congratulating yourself for code written well if it won't fit into the EEPROM when you're done. And one last thing I always try to fit into my code is a version number. I create the version number labels at the very beginning of the code where they're easy to update. And then I write those into the ROM at the very end of the code where they're easy to find in the EEPROM. I couldn't even estimate how many times I was getting nowhere trying to fix a bug in the software and then realized that I had been loading the same version over and over again. Now, once the program is assembled, I've been known to either hand enter the object code with my SDK85, but usually I put the code in an EEPROM or I just download it directly over a serial port using the Intel hex file format. I've done a video before on EEPROM programmers, but to sum it up, for EEPROMs that are 2764s or later that program under 18 volts, I use my XGECU, the TL8662. For 1702s, I use my Prolog M900 or my reproduction Mil Mod 8 system, or I also have Martin Eberhard's 1702 programmer. For 2708s, I use Eberhard's 2700 Orphan programmer. And then 2716s and 32s, I use my Willem PCB6 or my Needham EMP20. For the exotic things like the 8755s, 8748s, and so forth, I can use my Intel Intellect, but I usually use my Needham EMP20 if it'll do it. Using the Intellect is like driving a classic car. They're loads of fun and they really attract the women, but you need to be willing to delay whatever you wanted to do and sit down and fix it instead. On my project site, you can find reams and reams of code that I've written. I just wanted to point out a few commands that make the overall process quicker, simpler, and less prone to errors. So let me know if you see something in my code that doesn't make sense, and we'll see if we can figure out what I was doing at the time. I think that's enough on my workflow and how I set things up. Let me know if I left out some important gaps, or maybe you would like to share some suggestions or tips or tricks of your own. I hope at least part of this was useful. If it was, remember that this channel is not monetized. It's entirely powered by likes, shares, and subscribers. Thanks for watching. I will talk with you later. Bye-bye.